So yes, you are in broadcast now. Hello everyone. AWS user group community welcome you all to yet another interesting session to help you build more on AWS. Today, we are delighted to host Mr. Yan Koi.
Hey guys, so should I start now?
Yeah.
Okay, cool. All right.
So,
So in that case,
Yan, I would like to introduce Yan Kui, and we are very delighted to have him here for today's session. Yan is an experienced engineer who has run production workload at scale in AWS for over 10 years. He has been an architect and principal engineer with a variety of industries ranging from banking, e-com, sports streaming to mobile gaming. He has worked extensively with AWS Lambda in production and has been helping clients around the world adopt AWS and serverless as an independent consultant. Yan is an AWS serverless hero and a regular speaker at user groups and conferences internationally. He is also the author of Production Ready Serverless and co-author of Serverless Architecture on AWS, second edition by Manning Publications. He also keeps an active blog at theburningmonk.com and publishes a weekly podcast at realworldserverless.com. Today, Yan is going to share his 2 cents on patterns and practices for building resilient AWS serverless applications. Yan, over to you now.
thank you, Deepali, and hi guys. Good to be back here. Hopefully this week we can actually go ahead with the talk with no problems. So let me just quickly share my screen with you all, so we can get started. All right, I think you can see my screen. So here it goes. So let's start this session on how to build patterns and practices for how to build resilient service applications. And I think a good place to start is probably just to define what do I mean when I say resiliency. And if you look at the Oxford Dictionary, the definition for resiliency is the capacity to recover quickly from difficulties or toughness. And notice that this definition doesn't say that it's about preventing failures, but it's rather resilience is about being able to recover from them. And that's an important distinction to make, because as Werner Vogel, the CTO for Amazon, often said that everything fails all the time. So you can't prevent failure. It's not something that you can, that's within your ability to do. It's outside of your control. But what you can do is build applications that can withstand failures and continue to operate even when they happen. So in the data center that Amazon or Google or Microsoft is operating, you can bet that hardware failure happens all the time. The servers just suddenly dies, or particular rack would suddenly die. You can't, one of the things you learn really early on when you're building stuff on AWS, on EC2 and so on, is that, well, if you want something to stay up, you can't just run your application on one server, because when that one server dies, your application dies. And then you run, and then you decide to, okay, that means we need to run application in on multiple servers, potentially spreading out across multiple data centers, because it turns out other things that are outside of your control, like natural disasters or power surge, or even I think one time there was a shark that bite into a cable, underwater cable that connects different data centers together within AWS. That caused a network issue that happened in one of the AWS regions. Turns out entire data centers can go down even when you're running the cloud. So you want to run your application across multiple availability zones, so therefore data centers, as well as multiple regions within AWS. And then when you look at it on the sort of more individual, individual servers, you've got a bunch of resources that's available to handle requests that's coming in. You've got CPU, you've got memory as well. And of course, more requests coming in and hitting the same server means that you're going to use more of the available resources you have to handle them. And what you typically see is that, well, everything is kind of getting slightly slower as you hit, as you get more and more traffic, until you hit this certain point. This is what we call saturation points, whereby the latency for those requests just going to spike up. You just go up really, really quickly, because your CPU, your resources are now being overloaded, and you're not able to effectively process those requests. And of course, requests are still going to keep coming in, so you're building up a larger and larger backlog, and so your overall latency just keeps going up very, very quickly. And this happens on the sort of individual servers. And unfortunately, as we're building more and more complex distributed systems nowadays, we often find is a user would talk to an API, user-facing API, and that API would call some other API, some other service to get some information, which oftentimes have to call another service. It could be one of your own services. It could be one of Amazon's services that they operate, such as DynamoDB or S3. And if one of these other services that's further down the core chain is having a problem, is having some kind of outage or a elevated latency, then those problems can often propagate back, so that the services that are not handling those failures properly, they will end up having errors, and then return an error response to their caller, and then eventually get all the way back to the customer, which gets like an error pop-up in the app. And of course, that just it's not very good user experience. So that really starts to hurt your users. And of course, nowadays, there's so much competition in terms of the tensions that your customers have, then it's very likely that your customer will just go to somebody else. And when you look at the sort of systems that we kind of use every day, your Twitter, your Netflix, and so on, they are just getting more and more and more complex. So these are what you call microservice dev stars, and this was circa from 2015. So I bet all of these systems are far more complex than what you see on a screen nowadays. When you see on a screen now. And of course, when it comes to building systems in a very resilient way, it means that these guys have to invest a lot of effort into making the applications resilient to all kinds of different failures that they can observe in production. So I guess a quick introduction about myself. My name is Yan Cui. I'm an AWS Serverless hero, and I've been building systems on AWS for over 10 years now across different industries, from from e-commerce to social networks to gaming and so on. And one of the things I've done, I guess, in the past with serverless and was moving a social network to run pretty much entirely on serverless in about 2016. And the last couple of years, I've primarily focused on working with serverless technologies within AWS. Nowadays, I spend half my time working with Lumigo as a developer advocate, trying to improve the state of serverless observability. And Lumigo is I would say, troubleshooting platform for serverless applications that make it really easy for you to debug issues that happen within your serverless application, even when it spans across all kinds of different things, such as API gateway, event bridge, kinesis, SNS, and so on. We try to make it easy for you to see everything that's happening within one transaction so that you can work out where the problem is. The other half of my time, I spend working as an independent consultant, working with clients all around the world, helping them adopt serverless and AWS successfully through training, through consulting, and sometimes working with clients to actually deliver an MVP. So going back to the whole topic of resilience, I'd like to point you to this diagram that was originally drawn by Uwe Fredrickson. I'm pretty sure I just murdered his name, so this kind of shows you the 4 broad categories of things that we should think about when it comes to thinking about resiliency. From the high-level architecture side of things, you want to build systems that are loosely coupled so that they have their fit individuals. Microservices should be self-contained so that if one starts failing, it shouldn't have an impact on others, so that you bring down every other service as well. So this is where if you have a distributed monolith, whereby you've got lots of different services all share the same database, then you don't really have that self-containment, whereby you have a single point of failure when it comes to, if the database is having a problem, all of your services is going to go down. And then you've got isolation in terms of bulkheads. Oftentimes you think about account level isolation, could be running different applications, different services on different AWS accounts, which you have some built-in isolation in terms of security breach, in terms of some of the service limits and so on, but also even lower level in terms of building your applications. So if you're running a Java application, maybe you can apply some ideas around, we can bulkhead certain threads within the thread pool so that one particular process can't eat up all the available threads on the server, which end up causing a downtime. And so when it comes to Lambda, you have a much better resilience, I would say, out of the box. For one, you've got some isolation already out of the box, where every Lambda function would have multiple containers. Each one of them would run only one request at a time. So so within one request, you have this isolated execution environment where you are not going to cause problems on other requests that are also happening concurrently, and equally functions are isolated from each other as well. To a very large extent, you do have some regional limits that you have to think about, which we're gonna get onto in a minute. And then the thing you get out of the box with Lambda is the fact that you get them, you get multi-AZ. So one function, when you deploy, it gets deployed to 3 different availability zones out of the box. And the same applies to many other services that AWS offers, such as API Gateway, DynamoDB, and so on. So you get all of this multi-AZ out of the box. And the great thing is that for services like API Gateway and Lambda, when you don't use them, you don't pay for them. So even though you're getting all this extra redundancy out of the box, you don't end up paying for them when you're not using those services. And so this is one of the often pain points of having a really resilient application that you have to run on EC2 or on containers, whereby for every extra level of redundancy with multiple availability zones, you are paying more and more for those idle resources that you're not using when there's no request happening against those different regions. And then when it comes to requests coming in, AWS handles all the load balancing, so you don't have to build some load balancer yourself that sits across all of the different availability zones. And in terms of having a multi-region setup, you can also use the DynamoDB global tables, which we're going to get onto that in a minute, so that you can make it really easy for you to build a multi-region active application. However, as I mentioned just now, that you do have some regional limits you got to think about. In fact, every layer of this very common setup, I would say, when it comes to building a serverless application, where you have API gateway, you have Lambda, you have DynamoDB, all of these services have some throttling. So you can get throttled at API gateway, you can get throttled at Lambda layer level, you can get throttled on DynamoDB as well. And in terms of the sort of different timeouts, you also got to think about the fact that different services have got different timeout limits. So for API gateway, you have integration timeout for 29 seconds, but Lambda function can run for 15 minutes. So if you had configured your Lambda timeout to be greater than 29 seconds, then that means even if your function is still running, API gateway would have timed out the request after just 29 seconds. Equally, you've got SQS queues, which has got a maximum of 12 hours for visibility timeout, which is the amount of time the SQS will hide the message after it's been received by one of your processes, and before it's made available to another process for reprocessing. But your Lambda function would have timeout after 15 minutes. And the general recommendation from AWS is that you should set the visibility timeout to be about 6 times of your Lambda timeout. So if you are setting a Lambda function timeout to be, say, 30 seconds, then that means you should set the visibility timeout for the SQS queue to be 30 seconds times 6, which is going to be 3 minutes. And one of the common sort of practices or pattern when it comes to, well, we've got this API and it's going to do some pretty heavy computation, and API gateway is going to time out after 29 seconds, and we're not sure that all the computation is going to be done within that 29 seconds. So one of the patterns for sort of mitigating this particular risk is, well, instead of doing the work straight away, what we can do is especially in the case of a file forget, what we can do is we can accept the request from the caller, and then we're going to, instead of actually doing it in the function itself, we're going to just put it into a queue, and then have the SQS queue be trigger a Lambda function to then process them in the background, which in this case can take up to 15 minutes, and we don't really care because it's happening behind the scenes. And then you can also set up a delta queue. So in fact, whenever you are using SQS with Lambda, whenever using SQS, you should have a delta queue as well, so that if there's persistent problems with particular messages, like a poison message that you can't process, doesn't matter how many times you retry, then they don't just keep on using resources within your system, and instead, after a few retries, they're going to get captured by the delta queue. So in this particular setup, you can then absorb all downstream problems much better, because you don't have to worry about failing and then returning a 502 to the caller, because now you're processing stuff in the background. So you have a lot more flexibility in terms of how do you handle those kind of downstream problems. However, even when you do have a delta queue set up, you do, and then maybe something's happening. So it could be a case where you are talking to a third-party service, and it just so happened that they're having an outage, and you just keep on retrying those failed messages, but they're still having a problem, and that may take, I don't know, half an hour for them to resolve, by which time a lot of your messages would have gone into the delta queue because it's exhausted the total number of retries. So now you've got alert, and then you look at the delta queue and see, okay, I've got a bunch of messages. So now I figured that, okay, it was related to this downstream system having an outage, but what can I do to recover? So I need to have some way to replay those events, maybe put them back into the main SQS queue to reprocess now that the downstream system has come back live. So how do I go about doing that? This is quite a common problem that people run into. In fact, I've run into this quite a few times. So I built a set of tools broadly under this thing called the Lumigo CLI command tool. And one of the commands is available in the CLI tool is for you to replay messages from an SQS delta queue, and then put it back into another SQS queue or SNS topic or Kinesis stream, and you can even put them into a different region, or a different account altogether. So this is where potentially you want to try out first in, let's say, like a dev account before you replay them. And in this case, you have a separate toggle they can use to say, okay, please keep the messages after you replay them, because we want to just replay it in a dev environment to make sure that maybe it's a problem with our code, that we've actually fixed the problem before we put it back into the main queue in production, and then it end up failing again. So this approach, this very simple pattern, is very effective, especially for those find and forget tasks that you receive from like a post command, for example. But what happens if the caller is actually waiting for response? I mean, we can't just send the stuff to the queue and then process them in the background while some user is still waiting for response in the UI, because again, we are bound by that 29 seconds timeout on API gateway. So very similar, I guess, related pattern, which I think is called the decoupling invocations, based on where I saw it being formalized in the SOA patterns book, whereby, okay, you've got an API that accepts this request to do some work. The caller is expecting a response, but it's going to take a bit of time. So what you can do is, again, you're going to put it into the queue to do it, to process them in the background. But instead of just returning nothing, you return a 202 with a header, a location header that says, okay, when the result is ready, it's going to be at this location. So now the client can poll at that location from time to time to see, is the result ready yet? Is the result ready yet? And every time while the result is still not ready, they're going to get 202 back, and then again, just location header again. And once the work is actually being done by the background process, then the next time the client polls, they're going to get a 200 OK, and then they're going to get the actual response from the work that's been produced by the background worker. So if you walk through how this may look like, so here we got API gateway, we got Lambda. When a request comes in, we're going to put some metadata into DynamoDB table to say, okay, this is the request when it was created, and the current result is no. And in the meantime, we're also going to put a message into a SQS queue, and then we're going to respond to the caller with a 202 with the location header. So now with that, we've put the message into SQS queue. It's going to call a Lambda function, and the Lambda function is going to be doing stuff in the background. And in the meantime, if the caller pings the location and see is the result ready, we're going to see in the DynamoDB table that nope, not ready yet. So we're going to return a 202, and then the work is done. The background Lambda function is then going to update the record and set the result in the DynamoDB table. So the next time the client calls, we can see, oh, the result is there. Great. We're going to return that result to you in a 200 response. So this works quite nicely, but wait, there's still some problems, or at least the things that I don't really like about this. Firstly, we've got a distributed transaction here. So anytime you have, say, a Lambda function having to do multiple things within one request handling code, you have a distributed transaction on your system. So in this case, if, say, we first write the data into DynamoDB, and then we put a message into the SQS queue, well, what if the put to SQS fails? What do we do then? Do we just let it fail, and then we end up with a message that's sitting in the DynamoDB table that can never be completed because we never managed to queue up the task? Or do we have to do some rollback and then delete the data from DynamoDB? Ideally, you will need to do that. However, what if we are also running a pretty high scale and pretty close to DynamoDB's provision throughput, and then when we try to roll back, that fails for some reason, and then our function gets timed out after 6 seconds or 3 seconds? What happens then? We're going to end up with some phantom data. So when it comes to actually handling distributed transactions properly, you need to do it well and do it properly. You're probably going to have to end up implementing some kind of a Saga pattern, which we're going to talk about in a minute. But for now, one of the things that I guess one of the patterns for getting sort of working around the fact that you need distributed transactions here is to just use DynamoDB streams. So instead of having the first function doing both writing to DynamoDB and queuing up the task in SQS, you can have another Lambda function listen to the stream from the DynamoDB table and then say, okay, right, when someone when someone inserts a new task, I'm going to turn that into a message and put it into SQS instead. So that way, you don't have a distributed transaction anymore because it's all been sort of linearized. It's been sequentialized instead. And instead of putting something from the table into a queue through the stream, maybe you can just have the function do the work there and then. And one of the interesting things you get with these streams as event source, that includes both DynamoDB streams as well as Kinesis streams, is that you get this retry until success behavior, which is quite interesting. It's got some interesting implications and use cases. So, for example, the fact that you can with Kinesis streams at least, you can control how many concurrent executions are happening at the same time using the number of shards. But even without that, the fact that you get retry until success. So if DynamoDB streams calls your function and your function errors for whatever reason because the downstream system you depend on is having an outage, then your function errors. So DynamoDB streams is going to call your function again the next time with the same batch. You're going to do this over and over until you either process it successfully or until the data has expired from the stream. So that means when the failure mode here is that my downstream system is going to have an outage, you're going to have some problem, then, well, the retry into success just means that we're going to keep on retrying until eventually the downstream comes back, in which case we're going to be processing at the maximum throughput as dictated by the number of shards that you have in the Kinesis or DynamoDB streams. And so one thing to keep in mind here is how long the data is going to be retained for. With Kinesis streams, you can extend that to up to 7 days. With DynamoDB streams, you can't extend the default 24 hours retention, which means, well, this is all well and good and normal workday because you can't expect if something's happening, then it should be resolved within 24 hours. But for weekends, that might be a bit more tricky. So it may be that, okay, we don't have people on call or there's a problem, but no one noticed until Monday. And then by that time, a lot of data may have been lost already. So what you need to do is, what you need to make sure here is that you need to have good alerting in place so that when there is a problem, a persistent problem, that you get alerted quickly so that someone will go and address that problem. Maybe it's going to be a case of using the new features in the for stream processing. We're going to talk about in a minute, so that we set up a delta queue so that after a certain number of retries, those events get put into a delta queue instead. And also we have to worry about this fact that, okay, what happens if there's just like a problem with one message? Maybe the format or the data is wrong, and then we just can't process it. Every time we try, it just fails. Again, this is something we're going to have to deal with when it comes to the fact that it's keep on retrying until success. So a single poison message can essentially render your whole system unresponsive because it's going to keep on retrying this poison message without being able to process it and properly, and then it's going to not able to move on to the next message. So again, both things there are solutions to address this. But first, let's go back and talk about the fact that, okay, what if sometimes you just do need to have a distributed transaction? You just can't work your way around it anymore. So this is where you kind of you want to introduce the Saga pattern, which is a pattern for managing failures where within a distributed system where every action has equal and opposite compensating action for rolling it back. So if you want to learn more about the Saga pattern, you can go and read and watch this YouTube video afterwards. The link is through this link here. The example that Katie McCaffrey used in her talk there is a travel example where someone wanted to go on a holiday, which unfortunately none of us can now at the moment, where you have to have this transaction where you book a hotel, you book a flight, you book some car rental, and every single one of these steps can be modeled as Lambda functions, as well as every single cancellation step as well, to cancel the hotel, to cancel the flight, and so on. And to have that, and then for our Saga pattern, we need some kind of orchestrator or coordinator that sort of controls when do we execute the sort of the next step in the transaction, and then when do we execute the fallback logic. So we can use the step functions for that, and the step functions is great for orchestrating workflows with Lambda functions. So suppose the input here for our workflow is we want to book a trip from London to Dublin, and here's the details for the trip. In the happy path, we will book the hotel, that's succeeded. So we book the flight, that's succeeded, and then we book the rental, and that's succeeded. So we complete the whole transaction happily. In the failure case where we try to book the hotel, it failed for some reason, then we need to apply a rollback to cancel any sort of changes, any state changes that we've made so far for this booking, and then we're gonna execute the cancel hotel step to do that, and then we're gonna fail the transaction. Equally, when we book the hotel, that succeeded, but then when it comes to booking the flight, that failed for some reason, then we need to first cancel the flight as the rollback, and then we're going to cancel the hotel as well, so that we don't leave any sort of half complete the transactions in the system somewhere, and then we're going to fail the whole transaction. So going back to the poison message, the fact that the retry to success has got its benefits, but also the downside as well in terms of having to deal with poison messages. So really luckily, at the reInvent last year, Amazon announced a bunch of new options for managing this retry behavior you have for Kinesis and DB streams with Lambda, whereby you can configure this on failure destination. Essentially, this is your DLQ support for Kinesis and DB streams for Lambda, where you can say after the maximum retry attempts, which the default is 10,000, and this probably is way excessive for anyone's needs, I think. So I typically go with a retry attempt of 3 or 5, which is giving every message a reasonable chance to succeed. But if it still fails, then what you can also do is is quite nice, is you can enable this split batch on error. The fact that Kinesis and DB streams are batched event source for Lambda means that you're going to get a batch of, say, I don't know, 100 messages, or 10 messages, and only one of them was a problem. Rather than taking all 6 and then put them into the data queue, you can instead use this so that when you get that first batch of 6 and the error, the next time DB calls your function, it's going to split the batch in half and then going to give you the first half, which is 3 messages. If it failed again, you're going to split the batch again, and then this time it's going to give you the first message. And if that first message is the problem, then you're going to keep failing on that first message, and then after the maximum number of retry attempts you configure here, then that single message is going to be put into the delta queue. So using this split batch on error option, you can converge on the single the poison message very, very quickly. But the fact that the retry attempts only count when we're talking about just exactly the same batch. So when we go from 6 to 3 to 1 to 1 to 1, only the batch of 1, those count as the same batch. So the retry attempts only counts those, which means that overall you're going to have some of those messages be processed multiple times anyway. So you still have to think about idempotency when it comes to dealing with these particular partial failures. And also, when you eventually identify the poison message, it ends up in your data queue, and the data queue is the message is gonna look something like this. The key thing to note here is that you don't actually get the message body. Instead, you get information about where to find that message based on the shard ID, the sequence number as well. And so you have to actually make a call to DB streams or to Kinesis streams to actually then fetch the message body in this case. And remember, they're only going to be in the stream for, say, 24 hours for DB streams, or up to 7 days if you opt for extended the retention and pay for it on the Kinesis stream. So you do still need to have the alerting in place so that you can do this proactively before the data gets expired from the stream, before you had a chance to actually fetch it. And And whenever you're doing any kind of background processing, you always have to worry about, okay, what if there are more messages coming in than I'm able to process, especially when the failure case here is that, oh, no, we have to talk to some third-party system. And normally they respond within 5 milliseconds, and now suddenly they respond every request in 100 milliseconds. So now we are processing messages slower. It's not necessarily causing errors per se, but it's slowing us down. That means that our backlog is getting bigger and bigger, and we are not able to process messages fast enough to keep up with the rate of more messages coming in. So this is where you can use this maximum age of record configuration to say, well, when we're really overwhelmed by the amount of messages and we just can't keep up anymore, then what we can, and oftentimes you find is that, well, if the messages is not completed within a certain amount of time, the client or the user will just try again. So when they try again, the new message would you can just drop the old message and then prioritize the newer messages that's going to have a better chance to succeed here. And so those older messages that you're shedding, so this is load shedding we're talking about, is going to get put into the data queue. So you can still go back and retry them later if you want to. But in the meantime, you're able to then process fresh messages that when the user or the app just retries out automatically, hopefully you catch those newer messages that are, I guess, duplicates or retries of the original message. And then when it comes to load shedding, another thing you could do is, well, what happens if we're doing this load shedding, but then we're putting stuff into the data queue, and then we are still want to process them automatically, but we don't want to process it at the same time straight away, because that's just going to create even more traffic that's already causing us a problem. So whatever's happening with the downstream system, we're going to give them more traffic so that they're going to have even worse latency numbers or have more errors. So what you can do on those data queue, if you want to process them automatically, is add this delivery delay, so that you don't process them right away. Instead, you're going to process them with a slight delay. And when it comes to SQS, you also have to think about a slightly different, I guess, a partial failure case as well, because when it comes to SQS and Lambda, your function is SQS is still a polling-based service, except when you use it as an event source for your Lambda function, AWS is running this poller for you, is polling SQS on your behalf and then calling your function when there are messages, and then when your function completes successfully, then as the poller layer is going to call SQS to delete the message on your behalf. Now, what's going to happen if your function errors? Again, you get a batch of, say, 10 messages from SQS. One of them is a problem, and you couldn't process it. So even though 9 of the messages were able to, when it was processed successfully, one of them failed. That means the poller is not going to delete all 10 of them. So all 10 of them is going to get retried, potentially in different batches, different sort of batches to what it was originally. But in this case, ultimately, that sort of poison message is still going to be retried multiple times. You're still going to fail every time, and then it's going to be captured and then dropped into the data queue, which is great. But it's still a problem that the whole batch is now failing as a unit. So you are, those 9 messages that was fine and processed already is going to get processed again. So you have to think about idempotency, which can sometimes, it can be as simple as using conditional checks when you're using DB, so that you only update the record if the field, if a particular field or version number, whatever field you're using, is the previous version. However, that's not always the case, especially when you're calling third-party services. So there's no other way to really version them or make it idempotent. So I've discussed a couple of different approaches you can take here with SQS and Lambda, including just use a batch size of 1. The simplest approach you can take. However, there's no partial failure when the batch size is 1, right? However, this can hurt your throughput and add to your cost as well, because you're going to need more invocations to process the same amount of messages. And then the second option is to make sure that you have idempotency. Again, much easier said than done. Sometimes it's as easy as using conditional checks, but then oftentimes it's not. So my preferred approach is that, okay, So if that's not an option, then what we can do is we're going to process all 10 of them, but then we're going to have a try catch around every single message, and then we're going to just catch and return the failure response for every single message, so that at the end of the 10 messages, which is the maximum batch size you can have for SQS anyway, you're going to see, okay, which all the messages failed, and for the ones that failed, we're gonna leave them, but the ones that succeeded, we want to make sure that they are deleted. So what we're going to do is we're going to call SQS ourselves from the Lambda function to delete the messages that were successfully processed, only in the case where there was a partial failure. So now we've deleted the successful messages, so they won't get retried. And then what we can do is then we can just throw the error, cause a function to error, so you have some marker in your logging system to show, okay, one time this function errored, and then now those messages that failed would be retried with the same sort of mechanism that the SQS polar, the fact that it didn't call delete on the batch for you, so they're going to get retried later. But in this case, the ones that succeeded the first time around would have been deleted by you from your function. Another quite common, I guess, failure mode we're going to think about is what we call retry storm. So imagine lots of functions are talking to some service, and that service is under some pressure, so it starts to error, start to time out. So those Lambda functions, if you're using HTTP clients or using AWS, AWS itself has got built-in retry. So all these concurrent executions for your function are going to retry, as well as newer invocations. They're all going to try the same. They're going to do their first request. Again, systems have that service having problems, so some of these requests is going to fail, and they're going to retry again. And then alongside the next lot of concurrent executions, they're all going to try the same thing. So you're just constantly exacerbating the problem that you already have against this service A. So eventually that service is just going to crash and burn. And this is what we call a retry storm, where you've got the retries. So when a system is having problems, you have to handle the new requests as well as a retry from the previous request. And if those retries fail, sometimes you got retry again from the same request, while you have the second retry from the second batch, and then the new request, and so on. So a really good pattern for protecting against these kind of problems is to have a circuit breaker pattern, whereby you say, you know what, we're going to make a couple of requests to this service, and if this service at any moment in time fails, say, 5 times consecutively with timeouts or whatever or other errors, we're going to trip the circuit. And so while the circuit is open, the next time we're going to try to talk to the service, we're just going to fail. We're going to fail straight away without even hitting the service. But every couple of minutes or every now and then, we're going to allow one request to go through. And if that request was successful, that means the system has recovered, and we close the circuit and everything returns to normal. There's different libraries for implementing this logic in different languages. For Node.js, you've got this thing called Possum, which implements this logic. But when it comes to Lambda, a big question that you often have to ask is, well, that means we need to have some state, right? We need to know the state of the circuit. Where do I keep that? If I know, the simplest thing to do that is just put it in memory as your of the Lambda function. But a given Lambda function can have many concurrent executions. Every single one of them has got their own memory. And if you're putting stuff into global space as a global variable, whatever, well, with Lambda, you've got to remember that containers are retried, and anything that's outside of the handler function itself, anything that you declare as a global variables or as environment variables, they're going to get reused. They're going to get persisted between invocations for that same container. So if you're putting stuff in memory, keeping the state in memory, then they are going to persist between invocations. And so if you are starting to see failures and you're tripping the circuit, then that's fine. Then for that particular container, once you made a decision to open a circuit, then the next time that container runs is not going to try to talk to the service. So using the sort of in-memory state is very simple. There's really not much you have to do. A lot of the libraries already do this for you. And also the good thing is that there's no dependency on some external service to keep track of state, which you're going to have to, so for every service that you're talking to, you're probably going to want to have a circuit breaker to protect against that, so that in the case of problems, failures, you don't just keep hitting that same service over and over. So if you're using a database to keep the state, the state for the circuit, then again, guess what? You're going to need to have something to protect that database as well. And also, there's additional cost and maintenance in terms of the infrastructure, keeping things running when you don't use them potentially, and also managing permissions and so on as well. Now, the downside of this approach is that it's going to take you longer to converge on a decision that, oh, this service is having a problem, we shouldn't be talking to you at the moment. And since every container have to make a local decision to reach that decision, so they need to hit the service multiple times and have to fail a certain number of times before they each reach a decision that, oh, that service is having a problem, let's not talk to you anymore. And when you've got, say, a traffic spike and more containers came up, then well, guess what? They all have to each reach the same decision as well to not hit the service because that service is having problems. So all of this means that you are generating more requests to the downstream system in order to reach the consensus in order for each concurrent execution to reach the decision to open its own circuit. The other option is we can use some external service, and this could be as simple as a DB table, so that this table will just keep track of the state of the circuit, which right now is closed. But then after a few of the concurrent executions start to see errors, then they will report those errors to the database. And then if we see, okay, within, say, like a 5-minute window, we've seen 10 different timeouts from different concurrent executions, then we're going to trip the circuit. Now the circuit is going to be open. And next time, individual concurrent executions sees an error, is going to check, oh, is the circuit open now? Should I just stop making requests to the service? And then they can all find out from this centralized location whether or not the circuit is open or not. In terms of pros and cons, it's basically the opposite of what we just discussed. The pros being that you minimize the total number of requests you have to make you have to make to the service to trip the circuit. And then when you have new container that comes up, they can also just ask the database to see, okay, DB table to see is the circuit open right now, before you even have to make a request to the service that's having problems. The downside is more complexity in terms of the code, but also in terms of the provisioning of the resources, infrastructure, and the IAM and so on. And now you've got another dependency that potentially also requires protection through using circuit breakers. Imagine if so many things are talking to this database, this DB table, that becomes the thing that fails, and that's become a thing that you need to have a circuit breaker around to protect. In terms of which approach you should use, I would say it probably depends on how complex a solution you have, and also how much you care about just having slightly more requests hitting the service before you can reach the consensus that that service is having problems and how spiky your traffic is. But I'll tend to sort of go with start with the simplest solution for now, just at least at first, and just use the in-memory option. And if that you find, okay, that's just not clever enough, when it's something does happen, it makes too many requests to the downstream system, then at that point, maybe investigate seeing whether or not you can use another database to become like a centralized place to track this state. Another thing you got to think about when it comes to Lambda is how the auto-scaling behavior works. So Lambda auto-scales based on traffic. So if you call a function, it's gonna, and there's no container available, then Lambda is gonna create a new container, load your code, execute the request, and you just auto-scales based on traffic within some limit. So you have, firstly, you've got a regional concurrency limit, which for most regions starts with 1,000. That's a soft limit, so you can raise that to tens of thousands. There's no problem with that. However, there is a harder limit, which is how quickly you're able to create new containers across the whole region for all of your Lambda functions. And for most regions, again, that limit is 3,000. So that means if you need to have a peak capacity of, say, 10,000 concurrent executions, you can go from 0 to 3,000 straight away in most regions. Again, in most regions, not all regions, but in most of the bigger regions, you can go from 0 to 3,000. What happens then? You need to hit the 10,000. So that from then on, you can only go up, by 500 new containers per minute, which means to reach a peak capacity of 10,000 concurrent executions within the region, it's going to take you, let's see, 3,000 right away, and that means 7,000 at 500 per minute, which means it's going to take you 14 minutes to get to 10,000 concurrent executions. So for some of the traffic, it's probably okay because you don't have that spiky traffic. That's that spiky. However, you can. So this is basically showing how the burst capacity limits once you have goes over. What you can do is you can use a new feature, the provision concurrency, to say, you know what, I know I'm going to need 10,000 in a bit, so I'm just going to ask for it now. And provision concurrency behind the scenes is going to create those containers ahead of time, so that when you do need that 10,000 capacity, it's going to be there already. However, you're still bound by the same limits of 3,000 and 500 per minute. So if you know you're going to need a capacity of 10,000 concurrent executions, then you have to give yourself at least 15 minutes before you need that 10,000, so that there's enough time for provision concurrency to do its thing, to provision those actual containers and while respecting the 3,000 burst limit and then 500 per minute, so that it's going to take like 15 minutes to get to the capacity you need. And then with provision concurrency, and the nice thing about it is that you can do auto scaling. You can configure that with application auto scaling scaler, so that as you use more and more of your provision concurrency, you can also auto scale the total number of provision concurrency as well. And it also works sort of side by side with the on-demand concurrency. So if there's more requests than your provision concurrency is able to handle, then Lambda is just going to create containers on demand for you. So here's, I guess, again, a quick view of the limits we talked about, the 15 minutes, and the fact that you've got regional concurrency limit of 1,000 by default that you can increase with a support ticket. But then there's the limit of 3,000 initial burst limit, and then 500 per minute, which means that Lambda is great for spiky traffic up to a certain point. However, in practice, you oftentimes are not going to hit any of these limits because containers are reused. And if your function returns very quickly, that means if the average execution time for function is, say, 30 milliseconds, because all you're doing is talking to DynamDB, then what's going to happen is that same Lambda function, the same Lambda container, can handle over 30 requests per second. So that's basically 1 second divided by 30 milliseconds, you get 33 requests per second, which means even when you've got 1,000 requests per second, chances are you're only going to need 30 concurrent executions to handle that peak throughput. But still, there are systems that are just far more has got traffic that are a lot more spikier than that. It could be a case of e-commerce for Amazon and so on, where on Black Friday or big sales days you can have very, very spiky traffic. It could be Netflix when they launch a new show, or my previous company, The Zone, we do live sports streaming, and what we see is when this match is about to start, we got concurrent users going from maybe 200 to 1.2 million within 30 seconds, because everybody logs on like 30 seconds before the match starts. It's just human behavior. So in that case, we can use the auto scaling, built-in auto scaling with provision concurrency to say, well, we know when we're going to need it, but we know that the burst limit still applies here. So we're going to ask for the peak capacity that we know we're going to need, say 20 minutes or 30 minutes before we need it, so that there's enough time for us to ramp up to that total concurrent execution that we're going to need when the spike suddenly comes. And again, when we undercalculate it, then it's fine. It should be fine, because extra requests are just going to be handled by on-demand concurrency in this case. So that's all well and good for those predictable spikes. What about if you have unpredictable spike, like when the early days of Instagram, when Jennifer Aniston joined them and her first post took down the platform? Because again, a lot of these systems are social networks. You don't control what the users do, and when you've got a major influence doing something on a platform, that can create lots of unpredictable spikes. In that case, if your scaling problem is really with Lambda and the scaling limit, scaling limits that's in place for Lambda, then well, you can also just get rid of it. With API Gateway can actually talk to lots of different AWS services directly without having to go through Lambda. So if all you're doing, your API always doing is putting something into SQS queue, then you can also just have API Gateway do that for you using a service called using this thing called service proxies, which you can read about here in this blog post I wrote a while back. And if you're using something like the Serverless framework, there's also a very nice plugin that makes it really easy for you to configure those connections from API Gateway to, say, SQS, SNS, Kinesis, and so on. So I briefly touched on this at the start, that this whole multi-region active-active, which is kind of the gold standard when it comes to building really resilient serverless applications. So in this case, imagine you have a REST API with API Gateway, Lambda, DynamDB, all running in one region, and they're all sitting behind Route 53 with some friendly, user-friendly domain like api.myapp.com or something like that. This is already quite resilient because you got multi-AZ out of the box. But you still are vulnerable to region-wide failures, so that if the whole region is having problem, and sometimes you do have those networking issues that happens to an entire region, then what you can do is that you can deploy your application, the same application, exactly as it is, to 3 separate regions, and then you can serve requests from all 3 regions all the time in an active setup using Route 53 to route traffic to different regions based on probably using some kind of latency-based routing, so that user in the US would be routed to US East 1, or US East, or in the east part of US would be routed to US East 1. On the West Coast, they'd be routed to US West 1, and anyone else from Europe would be routed to EU West 1. In this case, you can still make sure that people can access data that are created by other users in other regions by making sure that all of your DynamDB tables, which again is a regional service, right? But you can link them, you can synchronize them using global tables, which basically is Amazon doing the data synchronization across multiple regional tables on your behalf. So in this case, if one of the regions is having a problem, you can enable health checks with these 3 records, so that when the region is down, that region is traffic is no longer routed to that region, and instead they'll be distributed to the EU West 1 and the US West 1 regions, so that even when there are regional problems, systems still just works automatically. Traffic will be diverted to the other regions automatically without you having to do extra things yourself. The same approach can be applied to data processing pipelines. It's not just limited to APIs. So for example, if you've got, say, 2 upstream SNS topics, again, active, so that everything goes to the US East 1 has got its own topic, and EU Central 1 has got its own topic. In this case, you have a queue, and then some Lambda function, and then that propagates some data into a DynamDB, which is then used to support some API you've got, which is why you've got these 2 different directions of arrows in this case. So in my single region, US East 1, I will subscribe to the topic in both US East 1 and EU Central 1, so that if one of the regions goes down from the upstream system, the whole pipeline still just works without having to do anything, any sort of manual intervention. So the fact that the system just continue to work stably without us having to do any sort of manual intervention is what Amazon engineers would call static stability using, availability zones, which again you can read more about in this article I've linked here. So this is basically how Amazon approaches building resilient systems that has got a static stability when certain regions or availability zones are having problems. But in this case, in this setup, you end up ingesting the same data twice, once from the different topics in different regions. So you do have to do some dedupe in your system, which could be, again, using conditional updates in the DynamDB, so that you don't write the same data twice into your DynamDB table. But if you want to take take your data processing pipeline and make it multi-region as well. Then you just deploy the same thing in a separate region. Again, now your queue in each of the regions is have to subscribe to both of the upstream regions as well. Again, and to do dedupe, and then you're done. DB table is going to be configured as a global table, so that again, Amazon is doing the data replication across the different regional tables for you. And in this case, if one of the regions goes down, EU Central 1 goes down, then all of your data processing pipelines in both regions are still working, because they can just end up consuming data for, updates from the US East 1 regions and SNS topic. And for the API layer, we already talked about how you can use Route 53 to sort of to route traffic to across different regions. So if if the problem is not with your application, it's not with your system that's not publishing data to the EU Central 1 region, but the problem is with AWS, that the whole EU Central 1 region is out for some reason, then doesn't matter. Your system is still working, because from the data ingestion side of things, well, the US East 1 region is still working, and is getting updates from the upstream SNS topic from the US East 1 region. And the API is still working, because Route 53 will just be routing all requests that was going to the EU Central 1 region, now all of them to the US East 1 region, so that you can, the system will still be working and have a static stability. But as you go into this world of multi-region architecture, there are things to keep in mind. While it's great, it protects you against a lot of regional failures, which doesn't happen very often, but when they do, they are fairly high impact. But at the same time, they do create a lot of additional complexities for you in terms of both how you write application, the fact that you need to do dedupe, the fact that you need to provision the same thing to different regions, which means CI/CD becomes a little bit more complicated, especially when you want to roll out updates. Do you update all regions at the same time, so that potentially if something goes wrong, you're gonna impact all the different users in all the different regions, and also it just becomes harder for you to test. Especially with this more and more distributed and complex systems, it becomes quite difficult to test them. And so the best way we have for testing these really complex systems is chaos engineering, which is something that maybe you have heard about from the likes of Netflix or Amazon. From how they talk about killing servers in production environments at random to simulate infrastructure failures, like that often results in the loss of EC2 servers, and see whether or not the system can still stay up when those infrastructure problems happen. It's certainly, like killing servers is certainly one way you can apply the principles of chaos engineering in practice, but chaos engineering itself is actually much broader. So in the words of principles of chaos.org, which is one of the best places you can go to actually read and learn about chaos engineering and really understand its core principles, it defines chaos engineering as a discipline of experimenting on a system in order to build confidence in the system's capability to withstand turbulent conditions in production. And notice that it doesn't talk about killing servers, it talks about a discipline of experimenting on a system in order to build confidence, right? And it's becoming increasingly important to companies all around the world, because we're just building more and more complex systems, which have more complex and hard to predict failure modes. And the thing about failure is that, as we talked about at the start, they happen all the time, be it hardware failures or software failures, and you can't choose when they happen. That they choose you. They just start to happen when they want to, and all you can do is choose how prepared you want to be when they do happen, so that your system, so they can build applications that are resilient and can still stay up when those failures does happen. And the goal of chaos engineering is to identify weaknesses in our system before they manifest into system-wide aberrant behaviors, because we fail to identify this systemic weaknesses early. And we do this by using controlled experiments to learn about how our systems actually behave when failure conditions happen. In the same way that we write tests for our business logic, we also need to write tests for our system's robustness and resilience against different turbulent conditions that is going to face in production eventually. And the two primary ways we can actually do this is through either organizing events like game days, where, for example, a bunch of you may gather together as a team, and then one of you would decide, you know what, I'm going to turn off networking on one of the servers, and then I'm going to see how quickly you guys are able to identify the problem, to see whether or not we have sufficient monitoring and diagnostic in place so that people can identify problems that they didn't know about beforehand, and then work out a solution for those problems. Or we can do it some more programmatically and in sort of automatic way to inject failures into our system to see how it actually handles them. And since you want to do these experiments in a controlled fashion, so that the experiment itself doesn't just spiral out of control accidentally and actually cause an outage in production and affect your users. And there's lots of different ways you can actually do this to keep a lid on the experiment and keep it under control. We're going to talk about that in a minute, and it's a very important topic when it comes to chaos engineering. But first, the 4 steps you can take to start doing some chaos experiments yourself. Step 1, you have to know what normal looks like for your system. If everything is on fire all the time, then you don't have a steady state, and you need to get your house in order first and establish what normal working condition looks like. For example, you may say normal working condition. Under normal working condition, the 99th percentile latency should be below 500 milliseconds. And there should be less than, say, 1% of HTTP errors per hour or per 5 minutes. And then once you know what normal looks like, then you can start to hypothesize or theorize what would happen if something was to go wrong. For example, if one of the servers in the cluster dies, or what if DynamoDB starts acting up and the latency starts going from a few milliseconds to hundreds of milliseconds. And then you can inject realistic failures into the system to simulate those failure conditions that you want to test. Remember, you want to keep them realistic. It's really easy to get carried away with, once you start doing these experiments, to hypothesize all kind of scenarios that's just highly, highly unlikely. We start with the low-hanging fruits. The simple errors oftentimes are going to give you the highest return on investment. And finally, after you run the experiment, go through the data to look for evidence to support or to disprove your hypothesis by looking at the metrics, the logs, the X-ray traces, and as well as any other forms of telemetry that you're collecting, to look for evidence that your hypothesis about how your system would behave is actually correct and true. And I can't say this enough, that if you're starting out, do this in a dev or staging environment. You can learn an awful lot from just running experiments in those environments. You don't want to go anywhere near your production environment until you are absolutely confident that whatever weaknesses you are injecting is actually being handled by the system, because you've done this so many times in the dev environment and in the staging environment. Think of it as if we were to perform, I don't know, martial arts on stage. Would you do that before you have practiced the same moves hundreds of times in the gym, or in front of the mirror, and instead of just go straight on the stage the first time you try something? You wouldn't, right? And remember, the goal here is not to actually break production. The goal is to identify weaknesses before they actually happen. And not to actually cause an outage that puts you on the front page of newspaper because your experiment has gone wrong and you took down your system, your service by accident. It'll be incredibly humiliating and quite embarrassing, and probably rightly so as well, because common sense would have told you to practice this in a low risk environment first before you start and you go and start killing things in production when you have just no idea what's going to happen. But despite the risk, you need to understand that the problems that you do find with all these experiments, they're not caused by chaos engineering. The experiment just reveals weaknesses that you already have in the system. And what the experiments have done is reveal them to you before bad things actually happen, so you still have time to prepare for them. but there are still risks involved, even when you are just experimenting in a non-production environment, as you can probably still accidentally break your dev or staging environment, and that can have impact on your colleagues who depend on these environments to work. So you just need to have containment measures in place. Firstly, you want to make sure that you run experiments during office hours so that people are in the office and they can deal with any unintentional consequences quickly to minimize their impact. You also want to make sure that you over communicate if need be, to be very transparent. Tell people what you're doing, when you're going to do them, so that nobody should be surprised that suddenly they see some errors coming from your service because you're running some experiment without telling anyone. And also, if there are any important business days coming up, make sure you avoid them. So if your business is like the zone streaming live sports, then don't do anything before or during the event. Just apply common sense and don't take any unnecessary risks. And when you do make a change, make the smallest change you can. So when it comes to injecting failures, for example, inject failures to one API endpoint at a time. And if you're going to do this in like a shared environment, then do this to one request at a time. And lastly, have a rollback plan ready so that before you even start, so that in case, bad things happen, you didn't anticipate how the system behaves and how it fails, and before things escalate too much, you just stop the experiment quickly and roll back whatever changes you've made. And I cannot say this enough, do not start in the production. You can learn an awful lot from those lower environments, and by the time an experiment graduates to production, you should be very, very confident that the system is actually going to handle it. And you're only going to get that level of confidence because you have practiced this hundreds of times in those lower environments already. And the great thing about chaos engineering is that it's not limited to just your application. It can be applied to test your infrastructure, the platform itself, as well as the sort of people and processes that you have in place in your organization, using things like a game days to see whether or not when something does happen, are your people well trained and well drilled to actually look for the right information to figure out what the problem was. In terms of tooling, you probably heard about Netflix's Simian Army, where you have a bunch of different monkeys for killing servers, for injecting latency, for killing an entire availability zone, or even a whole AWS region. And then there's also tools that allow you to run, I guess, the chaos monkey logic through a Lambda function, so that you don't have to run a server just to be able to occasionally kill other servers. But no, working with mostly serverless technologies, so the question that I want to ask is, well, how do we then apply the same principles to testing our serverless application itself? Because, I mean, we don't have access to the servers anymore, right? The servers that are running our code are managed and run by AWS and hosted within their own VPC. So I can't just log on to the server and I can't kill it remotely. The good news is that, well, when you're using managed services like AWS Lambda, API Gateway, and so on, AWS is already doing all sorts of experiments to make sure that the Lambda service itself, as well as the infrastructure beneath it, they're all highly resilient. So as a customer, I don't really have to worry about individual servers dying or sporadic hardware failures, but I'm still responsible for my own application code, and I can use chaos experiments to identify weaknesses inside my application. For example, maybe I've misconfigured my timeout so that some user-facing API is going to time out if the internal API calls has got longer timeout than it does. So I'm calling for my API service A, I'm calling service B, and service B has got longer timeout. So my caller is going to time out first, which doesn't make sense here, right? Or maybe I'm missing some error handling, which is a very incredibly basic mistake to make and also incredibly common in practice. And in cases where a downstream system is having some outage, maybe I'm also just missing a trick here by not having some fallback strategy in place so that I can return either some cached or some default response, so that I can mitigate a cascade failure here. So Gunnar, who's also a serverless hero, he published a very helpful library that allows me to inject failures into a Lambda function. And I want to show you some examples of how this can look like in practice. For example, what's going to happen to our application if, say, DynamDB is having an elevated error rate? Well, we hypothesize that given the fact that the AWS SDK itself has got the built-in retries, then everything should be just fine. So let's see what happens if that is indeed the case. So I want to switch quickly to a demo app. In the meantime, I just want to see if we've got any. Okay, we've got a bunch of questions here. Let me get back to the questions in a minute, but for now, I want to show you that. So this I've got this demo app here, and let me just see. There you go. It's not here. So this is the actual code behind it. Let me make it a bit bigger so it's easier for you to see. So it's a very simple project using the server framework. You've got like get index function that's doing some server-side rendering, and then you've got some permissions to call some restaurant API endpoint to get some to return the restaurants you see here. So when I load this landing page, this hits the get index function here. And then this API, this function calls another endpoint to actually get the list of restaurants that you see on the page here. And then that's the endpoint. That's the function that supports the endpoint that returns the restaurants. So very, very basic. But what I want to show you is that this using that library that Gunnar provided. So if open up again, go to package.json. So the library is called the Failure Lambda. It's a library for Node.js, but I think and for Lambda functions. But I think he's also got libraries for Azure functions as well. So what this thing does is within my say get index function, I have to require the Failure Lambda module, and then I use it to wrap my handler code around. So that's it. And then I have to say, for this function, provide a parameter that points to a parameter in SSM parameter store. So if I go down here, you can see the definition for that, which is something that is going to put into SSM parameter store, and it's going to look like this. So by default, it's been disabled, and you can inject various different kinds of failures. So in this case, what we're going to do is let's simulate what happens to our application if, say, the get restaurants function, the one that returns the list of restaurants behind and restaurants endpoint, if that's the one that talks to DynamDB to this restaurants table. So what happens if DynamDB is we're not able to connect to DynamDB? So I can do what I can do is I can go to SSM parameter store, go to make this a bit bigger as well. Okay, that's big enough, I think. Go to the configuration. I have for get restaurants function, and I'm gonna say the failure mode is to blacklist S3 and DynamDB. Okay, great. So I'm gonna edit this and I'm gonna enable it. Save. So now if I go back to the landing page, if I refresh, remember the hypothesis is that there's built-in retries, right? So it should just work. Indeed, it does, and that's because I think I've deployed the branch that's already got the thing. Yeah, oops, hold on, let me. So I already deployed a branch with the fix that's more resilient. So let me, hold on, redeploy this. And in the meantime, let's see if there's any questions while we do this. Okay, we've got a question from Sarab. How much max memory we can use in Lambda? So the max memory is 3 gig. And when you allocate more than 1.8 gig of memory, you also use a second. You can also get a second CPU core as well. However, when you're using languages like Node.js, which is single-threaded, you can't really take much advantage of that. And the Yeah, Nitin already answered that. But for languages, other languages like Java, .NET Core, oops, other languages like .NET Core, you can actually, or Go, you can actually access the second CPU core once you allocate the more than 1.8 gig of memory. And the amount of CPU you get, as well as the amount of network bandwidth you get, is also relative to the amount of memory allocated to your function as well. Again, depending on what your function is doing, if all your function is doing is talking to DynamoDB, then more CPU is not going to help you, because you're going to be waiting for I/O anyway. Good question here. Hi, how can we have different versions of Lambda to be promoted from dev, UAT, and production? So using the server framework, for example, you can see you've got the stage. So when you look at the functions that are deployed in the actual AWS console, so what I would say is that using tools like Serverless framework and other frameworks, they kind of do this for you. If I've got different stages, they will have they actually deploy different functions altogether. One of the problems you find with the fact that with Lambda, even though you do have versions, so if I go into one of these guys, I can see in terms of quantifiers, I do have different versions. However, all of the different functions should end up with the same IAM role. So if I change my code to require that requires more IAM permission or less IAM permissions, then that's going to be a problem for me. If the same IAM permissions are going to be used across different versions. Still deploying, so typically with the server framework, you can say SRS deploy, and then you can say I want to deploy to --stage or just -s. Staging instead, by default, it's going to use the dev stage. And then if I want to go to production, I'll do this. And of course, I'll have different IAM profiles, which if you use the Lumigo CLI, we also have a command that allows you to easily switch between different profiles. So for example, I've got a bunch of different profiles I use for different projects and so on. Also use the Lumigo CLI. Whilst we wait for the deployment to work, I can also use the Lumigo CLI to help me right-size the memory allocation for my function by using PowerTune Lambda, and say the region, say US East 1, and the name of the function. I've got a test function called the Python test. What this is going to do is it's going to strategy. So this basically execute different memory settings for my function to see which memory setting gives the best. Say in this case, different strategies, either cost, speed, or balanced. Most of the time, you want to go with balanced. When I do this, what it's going to do is it's going to deploy this thing that's created by Alex Casaboni, Lambda power tuning, Lambda power tuning, I think. There you go. So Alex Casaboni, who works for AWS now, he's got this tool that allows you to basically run different memory allocations for your function and figure out what's the best memory allocation for you. So when I do this, so after running that particular function, it tells me that the best memory allocation for my function, given that I'm looking for a balanced profile between speed and cost, is 256 meg. And I can say yes. And that's going to show me a diagram of how the performance changes over different memory allocations and how the cost changes as well. So in this case, you can see that by going from 128 default to 256 meg, by going from 128, not a default for the server framework is 1 gig, to 256, I can get a lot of performance improvement, but not so much change in cost. So that's why it recommends that as the best balance. Whereas if I go with the default, then there's actually no benefit, even though I'm going to be paying 4 times the cost per 100 milliseconds of execution time. I don't get any benefits from extra memory. Okay, so that's a nice bit of sidetrack whilst I deploy the others. Okay, so that's done. So let me. Okay, so this version doesn't have the fix. It's timing out, even though AWS CK has got supposedly retries. So let's look at the logs for this get restaurants function that we just invoked. So look at the latest logs, and you can see that we intercepted network connection to DynamoDB. So even though, as you can see, there's multiple attempts from the function because it's making multiple attempts from the SDK, when there's a persistent connection, persistent problem, the function still errors. So let's go back. So the result from that particular experiment is that our function still timed out after 6 seconds, and somehow our hypothesis was disproved. So what we learned was that you saw there's about a total of 10 different attempts. So the Amazon's DynamoDB SDK client has, for JavaScript at least, defaults to 10 retries with a base exponential backoff delay that starts with 50 milliseconds. And that delay between every retry is calculated using this particular formula, which Mark Brooker, who's senior principal engineer at the AWS, he kind of confessed at the re:Invent last year that this is his favorite formula of all time. So what that means is that if you put them into maths to work out what's the maximum possible delay after every retry, you can see that very quickly, just the delay between retries alone can push you over the 6 seconds if you have a couple of throttle exception. In this case, we had quite a few. We had more than 5, I think. So what can we do here? Well, one of the things we could do is we can just override the default configuration and set a more reasonable max retry count for our functions. Excuse me. And then we can also add the fallback. So for reads, we can fall back to previously cached responses or some static default response. For writes, we can queue up the write to a SQSQ or something like that, so that it gets retried in the background, similar to what we saw earlier in terms of what if you got a find and forget pattern a request from the caller. So let's see how I will fix this. So I've got actually a branch that addresses this particular problem, this particular weakness. So now, whereas before, let me just switch it back so they can see the before. So before, the get restaurants function looks like this, where you just call the get restaurants, which just get it from DynamoDB, do a scan, which you shouldn't do, but this is just a demo. So it just always is doing is this. The DynamoDB SDK itself has got a retry, so it's doing in this case a retry many times. This time I think was it 4. So they did a total of 9 retries attempts, and towards the end you can see it was the time between each of retries are very short before, and then as you get towards later on, the gap becomes a bit bigger. And so in any case, before all the retries are exhausted, our function has timed out after 6 seconds. So in this case, what can we do to make this better? Let me just quickly switch over to the other branch. So to make this better, what we can do is we're still going to call DynamoDB. We're still going to use the SDK to call scan. But what we're also going to do is we're going to just remember the last response, just going to cache it for future sake in case we couldn't talk to DynamoDB. Somehow we lose access to connections to DynamoDB. So, and this, as I mentioned earlier, anything that you declare as outside of the handler function itself, these are going to stick around on the same container. And I can also override the default max retries and turn it into 3. So after 3 retries, for some reason, it's still failing, then don't even bother anymore. So in my code here, I'll say get restaurants, but if after maximum 3 maximum retries, we're going to come down here, we're going to get into the cache block, and we're going to see, maximum number of retries has been exceeded. So if we have a response cache, because we had a previous response, good response, we're just going to return that. even if there's newer data, it doesn't matter. If return, if there's there are persistent problems, returning something is better than returning nothing. Otherwise, we also have some default set of response that we have configured down here, which is default set, which in this case returns 4 rather than the 8 restaurants we had earlier. So let's deploy this. And whilst it's happening very slowly for some reason, I'm gonna probably because I'm running streaming and video recording and also the bandwidth is taking a hit. So let me just answer a few more questions. What happens if an individual service goes down, but other services are up? DB is down, but if a gateway is up and running, exactly what we're trying to do here. So what we're kind of trying to simulate is that if DB is having a problem, but everything else is still working, so how can we keep the system running? One of the things we can do is to just do simple things like having some cache responses and having some default response. So one good example you probably have heard in the past is, Netflix, for example, in the very early days of Netflix, when you go to the homepage for Netflix, they try to load your profile and then give you your personalized list of videos or films you should watch. But if there's anything going on, there's any problems along that call chain, then you just get 500 and the website just crashes. So very early on, they realized that's just not a very good user experience. So what they did was, in that case, well, they basically applied the same approach. They have some cache for previous responses for you. So if they can't talk to the profiles service or whatever the service they called it, they return a cache response. If failing that, they don't have any cache response for you, then they just return a default set of films that they know everyone is able to watch. I think, if I remember correctly, from a previous talk they did, it's like films from the 1980s, because all the copyright has expired on those, so that they don't have to worry about showing you movies that you may not be allowed to watch in your country and things like that. So that's basically a similar approach that the Netflix does as well. They've actually done a lot of work. I think they probably moved on from that now. But now, but on the Netflix, they used to have this library called Hystrix, which has got this sort of fallback pattern back into everything they do. So every command they do has got a fallback, which could be getting data from the cache. And if that still fails, then the fallback will be, they will bake some default response. So in this case, we've deployed our app. Let's make sure it's still working. Okay, so now this is returning a default set because we don't have any cache response, and because we have this guy set to true. So we're not able to talk to DB, but we're still able to respond something because we have some default response that's baked into the system. So let's see what happens if we disable this. Maybe let me just touch this function. Another thing to keep in mind is that whenever you change the function's environment variables, it essentially causes it counters the deployment too. So now we've got a fresh container. The next time we run, there's no errors. Fresh container is going to run. It's got all the data back from the restaurant's API, so it's got a cache. So now if we go back to the SSM parameter store and we turn on the failure injection, save it. Notice I took a bit longer, but it still returned everything. So let's look at the logs for this get restaurants function. Look at the latest one here. So the first time we ran, it got all 8 restaurants from the DB table. Second time we run, after 3 retries, because we blocked the network connection to DB. So it says max retries exceeded, executing fallbacks and return the cache response. So even when we're not able to talk to DB, the system is still working in this case, which I hope also answers your question as well. So let's go back to the slides. So the outcome of doing all of this is that we end up with a more resilient system, which is what we're looking for here, even though our code becomes a bit more complicated. All right, so let's do one more demo, one more example, and then we can try to go answer more questions you have. So in this case, well, what if we were depending on a service and the service itself has got an elevated latency? So in this case, we've got the get index, we've got the get index function doing the server-side rendering and talking to another API endpoint to get the list of restaurants. What happens if the restaurants endpoint is having elevated latency? Well, okay, so suppose we have a try-catch around that, so we should be able to handle it around those API calls. So again, we can bake in some default responses and so on. So let's see what actually happens in this case. So let me go back to a version of the code that didn't have my fix. So if you look at the get index function, is calling the get restaurants function, and then is just doing some, well, I call it server-side rendering. It's not really proper server-side rendering. I'm just using Mustache to put a few restaurant stuff in there. But in any case, there's no error handling here. But even if we do put some error handling, I still wonder what's going to happen in this case if, say, the get restaurants function have started timeout. So one of the things you can also do with let me just copy the syntax, copy it here. So latency. So I wonder what happens if, so by the way, I forgot to mention, the rate is basic percentage from 0 to 1. So you can have, in this case, I'm saying 100% of the time, please inject error. But you can also, if you're going to be doing something on a sort of like a shared environment where you don't want to take down the whole environment, then you want to be dialing this down so that it doesn't happen for every single request. So if I go back to the get restaurants function, so configuration, and just change the failure mode all the way up here. So instead, if the failure mode is to inject some latency, so this injects latency to the whole function itself. So imagine if I just make the function really slow, as probably make it out of good. So now the get restaurants function should be very slow. So if I load this again, which you see in the logs, okay, that timed out, and that's probably because we injected some latency. In this case, we injected 6 seconds of latency and caused this get restaurants endpoint to time out, which causes the function that's doing the server-side rendering to time out as well, and which returns the internal server error. So the question is now, okay, that's obviously not good user experience. So what can we do about this? So one of the things that you learn quickly is that API Gateway has got integration timeout of 29 seconds. If you're using Serverless Framework or SAM, it's going to use the default timeout for your function, which can be set to like 3 or 6 seconds. But most HTTP clients itself has got a default timeout of 60 seconds. So before the HTTP client times out the HTTP requests, your function is going to have timed out long before that, and the API Gateway would have timed out before that as well. So what we can do is that we can set some timeouts for the HTTP requests, right? But the tricky question is, well, what timeout value you should use? I've seen 2 strategies to doing this. One is if you take a function that has 6 seconds of timeout, you can divide it equally across the different API calls it's making. So if this function is making 3 different API calls, then every request gets 2 seconds. Seems pretty fair. However, as you can see in this particular case here, even though overall we should have had enough time to execute all 3 requests, because one of them was slower than 2 seconds, we end up timing out the HTTP request and then failing the potentially the whole API function, like Lambda invocation. So we're not giving this request the best chance to succeed. Another approach that I've seen that's more optimistic is, well, if the functions go 6 seconds, we're going to assume that most of the requests are going to be quick. So we're going to use we're going to give every single request, say, 5 seconds. That should be enough. So long, one of them doesn't take that long. So in this case, even though none of them was longer than 5 seconds, but together they're all a bit slower, especially which is quite likely, especially if you're making multiple requests to the same service. So if you're making 3 different DynamDB calls in the same invocation, and the DynamDB is having some issues and average latency is up, then even though individually each request is not so slow, they get timed out. Overall, they still cause your function to time out before you're able to return anything. Luckily for us, when it comes to Lambda, we can actually find out how much time is left in the current invocation using the context object, which has got a property, a method called get remaining time in minis or something like that, which we're going to see in a minute. So a much better strategy, I think, is to set the HTTP timeout based on how much time is actually left in the current invocation, but reserve some time at the end so that you can do any recovery steps you like. For example, logging the timeout event itself, publishing custom metrics, or fetch some cache response from somewhere. That way, every request is given the best chance to succeed. But if they do take longer, they take too long, then we would time them out before they cause the invocation itself to time out, which end up with a 502 and going back to the caller and potentially cascade the error. So let's have a look to see how that can be done in code. So I'm going to switch back to VS Code, and I'm going to switch over to a branch. So I'm going to share the repo with you guys and the different branches that shows you how you can apply this in your own code as well. So again, we are calling the get restaurants function here by calling the HTTP endpoint, right? But in this case, we first find out how much time is left in the current invocation by calling this get remaining time in minis, and then divide and then minus the amount of time you want to reserve time, 100 milliseconds. So we're gonna use in this case I'm using Bluebird, which is a Node.js JavaScript library that also lets you manage promises a bit better. It's got support for timeouts and things like that. So in this case, I'm saying when I make the request to the restaurant's endpoint, please put a timeout on that. So in this case, the timeout would be whatever time is remaining in the invocation minus the 100 milliseconds. So when that happens, if it's successful, then we're going to set the response cache again. Otherwise, if the error is timeout error, then we're going to check, do we have a cache response already from previous invocations? If so, return that. Otherwise, return the default response, which again, something that we have configured here. So if I was to deploy this guy, I should be able to deploy a bit quicker if I just deploy this particular function. Index. So let's also maybe let's see what happens when I deploy this. So what I'm expecting here is that since we don't have a response cache, we are going to just get back the default response we get here, which is 4 restaurants. Okay, so while that's happening, I'm going to answer another question. Hi, what's your suggestion on lightweight Java web frameworks to be used with Lambda other than using Spring? So if you're using Java, you don't want to use the web framework at all. So when I'm writing Java functions, I just have the raw Lambda handler. So I wouldn't use the web framework at all. So if you do want to use the web framework, then you're probably going to be looking at, and you care about the latency or cold start latency, then you probably want to be using provision concurrency to make sure that you have warm containers always available so that your user doesn't see the cold start latency, which is going to be hugely impacted when using a web framework in Java, because that's just going to create so much classes for the class loader to have the load during a cold start. So now let's see if this works. So even though we are not able to get a response back from the get restaurants function, which let's see if I can get the latest logs. Yeah, the latest log says it injected 28 seconds. So clearly, our function, our get index function, didn't get a response from the restaurant's endpoint because it would have timed out. But because we have that error handling here, even though we don't have a response cache, we still return the default set of restaurants. So the system is still working, even though even in the face of inability to get the data it needs from the restaurant's endpoint. Okay, so that's how we're doing on time. Okay, we're running slightly over, but almost there. So the outcome of all of this is that we end up with a more resilient application, which is again what we're after here. So as a quick recap before I go back and answer more of your questions, remember everything fails all the time, or at least eventually for you. And the point of building a resilient system is not to prevent failures, but rather to build systems that can cope with and recover from failures quickly. And when it comes to Lambda and serverless applications, serverless technologies, you get a lot of resilience out of the box by the fact that you have a multi-AZ out of the box for services like API Gateway and Lambda. But you just have to think about timeouts, especially when different services has got different timeout limits. API Gateway has got a hard integration timeout of 29 seconds. Lambda got an invocation timeout of 15 minutes. And SQS has got a visibility timeout of a maximum of 12 hours. When you have tasks that are find and forget, rather than doing everything in the Lambda function itself, you can actually just put the work into SQS queue and then process it in the background, which give you a lot more flexibility in terms of handling and the retry and errors. And then you can also have a delta queue as well, so that if after say 5 retries, it still fails, then at least you don't lose the event. You capture that in your delta queue. That works well for find and forget cases, but for cases where the customer is still waiting for a caller is waiting for a response, then you can use a similar pattern called the decoupled invocation, where essentially you can queue up the task, but then you return to the caller 202 with a location header telling them where to find the result when it's ready. But the problem you often find is that you end up having to have some kind of distributed transaction, because you have to save the data in DB, but also put the task into SQS queue, and to sort of avoid often having these distributed transactions, you can use the DB streams to invoke a Lambda function to do the work directly. Keep in mind that with DB streams and the Kinesis streams, you have this retry until success behavior, which can be good for dealing with cases where, say, a downstream system is having an outage. So you don't have to do any work, essentially, to just use the retry and success until the downstream system comes back, then everything returns to normal. However, this retry until success also forces you to think about the poison messages and how to deal with them. And luckily nowadays there are more options that you can configure with Lambda and DB and the Kinesis streams on better handling them by configuring a lower retry attempts, as well as enabling split batch on error. And in cases where you may end up with a huge amount of backlog that you can't keep up with, you can also use this configuration to implement the load shedding, so you can prioritize the newer messages that has got a better chance of succeeding. In terms of retry storms, you can use a circuit breaker so that when the service is struggling, is timing out, is erroring, you don't just keep on piling up on that with more and more requests and retries on that service. Instead, you fail fast, but check every now and then to see if the service is back, and if it's so, close the circuit and things go back to normal. For cases where you can't avoid distributed transactions, you can use a Saga pattern to model your transaction and then to implement the action and every single rollback action as well. When you're dealing with batched resources like SQS, Kinesis, and DB streams, you have to think about partial failures. And for SQS, the best approach I've found is to try catch every single message And then when there's partial failures, then manually delete the messages that succeeded, and then bubble up the error so that you get those failed messages in another retry. It's worth thinking and learning about Lambda's auto-scaling behavior, and it's also how the provision concurrency works, which can be very useful for dealing with predictable spikes that would have otherwise caused you to run into the burst capacity limit in terms of how quickly you're able to scale up the total number of concurrent executions for your Lambda functions in the region. We talked about multi-region active-active, and that's the kind of the gold standard when it comes to building really resilient service application that can withstand not just availability zone outages, but also region-wide outages as well. And then we have talked about chaos engineering. We defined it as a discipline for experimenting on a system in order to build confidence in the system's capability to withstand turbulent conditions in production, and how it's more than just infrastructure testing or platform testing. It can be used to stress testing your application as well as the processes and people and practices you have in your organization. And with that, that's kind of everything I do have. I know we've been going on for quite a long time, and I really thank you guys for staying with us. As I mentioned earlier, I spend most of my time working as an independent consultant. So if you want to see how serverless can help your organization go faster, or need some help scaling up scaling up your team, then go to theburningmonk.com/hire me to see what services I offer and how we can work together. And I've also got a bunch of courses that are self-published. You can get some discounts on those courses with this code, which is just for you guys, so don't share them in public. Again, thank you so much for today, and we're going to go back and answer some more of your questions. So that's it for all the. So that's it for the I guess the main sessions I have, and let's see. Got a question here. If from within Lambda we want to invoke HTTP as endpoint and we get certificate error, then where do we upload the certificate in Lambda? There's no provision for key stores. That's a good question. I'm not sure. I got a question here from Hash Gupta. Between Java versus Node.js, what is more performant to be used with latest Lambda? Do you see some overhead with either Node.js versus Java? Where's your preference between these two? I would say my preference would be to use JavaScript. With Java and .NET Core, you just have a much higher cold start time because for new container, Lambda has to bootstrap a whole new JVM runtime and load all these different classes. And last question from Juju. You were talking about the sequential processing using DB streams and processing in Lambda. It can turn out to be disastrous if Lambda updates the same table back. So you're talking about, yes, recursive invocations. It can be, but it can also capture those as well. So for example, if you update your function, so if your Lambda function updates the same table but sets the status to a different value, then you can also just filter out those events so that you don't process them again. It's not just the DB streams. You can have the same thing with SNS topics. You can have the same thing with SQS or S3 files. I've seen people probably run into this far more with S3 files than I've seen them with DB streams. So I think that's everything. Actually, I don't know where's Dipali, but yeah, thank you guys so much today for your time today, and so I guess back to you, Dipali.
Thanks a lot, Jan. I think it was very insightful. I hope it is very useful for the audience here. Guys, please do share your feedbacks on the session. That will really help us to conduct future session. And I would like to thank Jan for your precious time and this knowledge you shared with us. Thank you so much. Have a nice day ahead.
Take care. Okay, bye-bye.
Bye.